All right, in this video we're going to talk a little bit about conservation of angular momentum. And to do that, we're going to talk about the last fundamental principle of mechanics, which is the angular momentum principle. So here what I have are two definitions that we've had in the previous videos where we talked about how we define the torque and how we define the angular momentum. Now, torques cause these rotations, so they actually cause changes in the angular momentum. So our observation is that if we're following the angular momentum of some system around a point, A, that it responds to that torque about that location. This is the angular momentum principle, which I'm going to call AMP, just to make it simple. Now, the angular momentum principle here tells us how an object is going to change its angular momentum in response to the torque. There's a full derivation given in the notes on how you get from the momentum principle to the angular momentum principle, but I'm not going to go into the details. What I want to get at is there are situations where we can pick a location A such that we have no torque, and angular momentum will then be conserved. So if you have a system with some choice of A where you can say the torque here is 0, the angular momentum of that system will be conserved. The initial will equal the final. So let's see a situation where that can happen. Let's be concrete about it. So we're going to talk about a comet going around the sun in an elliptical orbit. So here's the sun, here's the comet. And we'll choose the sun to be location A for the time being. And it's a very clever choice of the location because the position vector that points from that location to the comet points exactly opposite the direction of the force that the sun exerts on the comet. So as we talked about, when these vectors are parallel or anti-parallel, right? When we're talking about the torque, when we're taking a cross product, if these vectors are parallel to each other or anti-parallel to each other, you end up with no torque. So by choosing the location to be the sun, there is no torque about location A. So if that's the case, the angular momentum of the comet is conserved about that point A. So that means whatever angular momentum it has here, it will have that same angular momentum there around this point. And we can use that to make predictions. If you know how fast and you know where the comet is and how fast it's moving here. If I tell you any other location, you could tell me how fast it's moving, not from an energy perspective, from an angular momentum perspective, which is pretty cool. It's very useful for other types of situations as well. Now, if we were to choose a different point, let's be less clever, let's choose the other focus of the orbit, so location B here. If we choose location B, there's a vector that points from location B to the comet. Now we can see that there's going to be a torque exerted because the force is no longer parallel or anti-parallel to the vector RB. And so the torque about B, which is RB times the force, is not equal to 0. And so the angular momentum is not conserved. So when you're working these kinds of problems and you're thinking about how to employ angular momentum, particularly when you're trying to think about, say, collision problems or motion problems where you have angular momentum that can change about different points, trying to be clever about the point that you choose such that you get no torque and you can exploit angular momentum conservation is a really good idea.